Ed,
Ed,
good morning.
good morning.
Good morning, Anant. Good
It's
morning. A little
it,
earlier than our usual time, but that's
yeah,
good.
Yeah,
because Alessandro is
because
in Europe,
Alessandro is in Europe,
so
Yes, absolutely. Yes.
we're always ready
we're
to
always ready to
accommodate.
accommodate.
Our guests
Our
are at
guests
least
are
as
at least
important
as
as
important as
24/7.
huh?
I said 24/7. Wherever technology is taking, context window will be there.
We bring the
we bring
context
the
to
context to
absolutely. Okay, that's
absolutely.
As
Okay,
long as we don't start covering like space or something, and we have to go and do a podcast from the space station or something.
and that there, of
And
course,
that
as you
there, of
know,
course, as you know,
in 85
in
minutes
85
we'll
minutes, we'll
circumnavigate the globe.
circumnavigate the globe.
So
Yes,
we'll see all
we'll
24
see
hours
all
in 85
24 hours
minutes.
in 85 minutes.
Hey,
exactly.
so this is our last
So this is our
episode for the
last
year.
episode for the year.
It's just been
It's just been
fantastic. So why don't
fantastic.
you just
So
tell
why
us a
don't you
bit
just tell us a
about
bit about
what's coming up in
what's
this
coming up
episode?
in this episode?
Well, great. Well, so we've had a lot of folks. In fact, we've spoken to this a couple of times in previous episodes where the intersection of quantum and what's been happening with AI, what that looks like, and so now we actually have a couple of experts on that who we're going to get to talk to. Alessandro Curioni and Sarah Sheldon, two folks over here at IBM who have been doing really leading the charge from the standpoint of thinking about this stuff, and so that's going to be pretty exciting. And I think we're also going to kick things off by looking back on the year and some of the interesting things that have been going on, around AI in the last 12 months, which probably covers a pretty broad swath. So I think we'll end up not covering each and every little thing, but a couple of things you and I have observed.
Oh no, obviously, very painstakingly, highly scientific
Yes.
this process. We came up with two topics that we will talk about.
Exactly. We did a meticulous month by month analysis of everything that had been announced on AI, and that actually would be a ton of work. It would actually be a pretty good use for an agentic process. So in fact, maybe we'll do that before. Yeah.
Absolutely. I'll tell you later on about how I learn about Nobel Prizes using. But why don't we begin with kind of the first observation, Ed, that you had around scaling laws and what's really going on?
I mean, I certainly wasn't my observation. It was more that there's been a lot of chatter around scaling laws. Really, I think probably starting last year, and I think just from I think most people who follow us understand that one of the big catalysts that has made a lot of the things happen here was really the the approach of really using brute force compute at a level that I think a lot of people, a lot of scientists, researchers have not really contemplated as being practical. At training large models and delivering these services, and that's what's led to the GPU explosion that has powered a lot of this stuff. And there've been some folks like Gary Marcus and others that have been sort of naysayers all along, but you've seen now that that's picking up steam, and I'm sure you've seen the same thing around that.
No, absolutely. I mean, obviously. But what really caught my attention was not just naysayers in that sense, but really people who have been in this field, who could have won Nobel Prize like Jan LeCun, right, saying that, look, in order to kind of break through the barrier, we really need to think about it slightly differently. And obviously, he's been talking about, he kind of left Meta recently, and he's been talking about kind of the world models and everything else. So it looks like there are people who are beginning to explore and say, okay, now look, maybe this is going to get us, it has gotten us where it's going to get us, and we need slightly different paradigm to kind of break through that barrier.
Yeah, exactly. And it's going to be interesting to see. I mean, look, you know, I come more from the software standpoint, and my take is that in terms of the usage and applications and ability to harness this within agentic software, I think we're just scratching the surface. And I do think that oftentimes the researchers that are involved in this are actually several years out in what they worry about versus what I think is going to affect most of us. So when they start saying it's hit the wall, does that mean that your ChatGPT is going to stop working or agentic process? No, I think you've easily got a decade more on current existing model architectures and emerging software architectures going around those. But we'll see, and I certainly think that that these other approaches, world models, which depending on which of the three major definitions you follow, are all very exciting. And obviously, Jan LeCun is very smart, very, very smart person who understands this stuff better than any of us. And obviously, I think, Ilya Sustover made some similar comments, but from different directions a few weeks ago, and a lot of that. And so I do think it's interesting. Again, what I've tried to do over the last couple of years is to make clear to people that at the same time that you have these model advances, that we're still building the software architectures around that. I think at this point, we're still at the point where most software engineers are just understanding how to build an agentic loop or do a proper eval.
That conversation in quantum also, right?
Well, I think quantum is going to open the door on that as well.
No, I had not thought about it like that. That's an awesome point. Hey, listen, we can debate about $1.5 trillion of data center investment around current architecture, but let's move on to topic number two, because I'm very, very eager to have our guests on, because I think that it has blown my mind with respect to what quantum is all about. I haven't really understood it fully. I don't think anybody really understands it fully. But before that, agents is the answer to everything. But my observation was that the way it has kind of affected my life, your life and life of many countless others is around coding. So is coding the killer app for agentic AI, and will it kind of continue to be the killer app, or there'll be other things that will emerge?
I mean, it's the first killer app. I mean, to the extent that obviously I think ChatGPT and the chatbots general purpose have been probably earned the first killer app, but sort of the first killer app where I think from a
enterprise.
From an enterprise, from a cost benefit, from something you could build a business around where you weren't necessarily operating at a loss. I think that code assistance right now, apart from all the other hype, if we simply had code assistance emerge, and you had businesses that were looking to deliver code assistance, and that was just their pure focus. It was not for them, stopping point on the way to AGI or other things, that you would go and say, it is a killer app, right? Like coding assistance is like they, pick previous killer apps that desktop publishing, and now I'm sounding old, or spreadsheets, and now I'm sounding really old, or stuff within, mobile email, right? Like things that are standalone in terms of utility, in terms of benefit to the customer, in terms of the ability to serve them sustainably at a profit. Like I think they're the first killer app, and I think but are they last and only? No, they're just a great template for what it looks like And I think they're still early in their cycle. Like I think there's, so yeah, I would look to that as a great example of what the go forward may look like still in other disciplines, or maybe each area of work will require reinvention and so on. I don't know. That's literally the $1 trillion question that I think everybody is pursuing.
Absolutely. Somebody computed.
Trillion
sounds too low because it's 3 trillion, 30 million developers multiplied by 100K. So you can come up with any ginormous number out there. But I'll tell you this. I think that the two things that have truly affected how the way I work. One is whenever I'm kind of confronted with how would I think about something, I always interact with kind of a good chat client. In my case, it's Claude. And then when it comes to coding, right? So those are kind of two things that you pointed out are really in my mind currently the place where people are finding a huge amount of
and a huge amount of runway in terms of adoption ahead of it. I whenever I read, and there's a lot of folks and many people we know and so on who are still not sold on it, but I actually look at that and say, okay, I do think that eventually you are going to get to a majority situation where people are using these things. So I think there's a huge runway ahead of for that particular business, and I agree with you just from a personal productivity standpoint. The things that it makes possible to explore from a coding standpoint, just by sitting in there and getting into the discussion with Claude or whatever one is using, and the ability to prototype and honestly to solve real production problems, build tests, build new tools for it's just we could go on all day on that. So
anyway, those are our two winning stories. One is potentially question mark death of scale, and second is coding is the killer app. Okay, so now with that, let's kind of talk a bit about what we're going to talk next. So we have always known that GPUs have become kind of one of the predominant ways in which this new wave is happening. And the previous wave, of course, was CPU. But then all of us have heard about quantum. And the key question is how do these three paradigms kind of come together? Where does AI sit with respect to these kind of approaches? And we thought that we'll kind of talk to people who are experts about it. There are lots of talking heads. We are talking heads on many topics, but it's an absolute pleasure. So Hannah, if we can get a guest on. Hey, awesome. So again, Alessandro and Sarah, just absolutely phenomenal having you on. I'm not going to waste 7 minutes praising both of you, but IBM is just really big in quantum, and our quantum work is basically both hardware as well as how that hardware gets deployed and computation happens on top of it. And Alessandro and Sarah, geeks, nerds have really been thinking about that thing really deeply. And beyond holding PhDs, they're also distinguished scientists and fellows within IBM. So welcome to the podcast, Alessandro and Sarah. Absolute pleasure having you here. So why don't we begin first by demystifying quantum computers a bit for our audience, and for the two of us too.
Sure, I can jump in. Great to be here. And always happy to talk about quantum. So I think, where do we start with quantum? So the idea is that we can build computers that operate on different mathematics than classical computers. So, our classical computers made out of transistors, their mathematics they're based on is really arithmetic. And with with quantum computers, our fundamental unit, the bits, are quantum systems, and they operate according to the laws of quantum mechanics. So we can leverage this different mathematics
with voodoo math.
Yeah, so we can leverage this different mathematics to build algorithms in totally different ways than you could classically. So you're using these kind of fundamental tools of superposition and entanglement and quantum interference in order to build algorithms that can just map problems in a different way than you can classically. So we've known for a long time this is really what you're going to need if you want to, say, simulate another quantum system. So like if you want to study chemistry problems and you want to represent a quantum state, you really need a quantum computer. But we're also looking at other applications of quantum computers where you can leverage this different mathematical framework to do things that are hard to do classically.
Awesome.
Yes.
Go ahead, Alessandro.
Yeah, and look, people when discuss or speak about quantum, they look at these at probably different or new accelerators that in the future is going to help us, to do certain things much faster. That is one view. I do believe that what is going to happen, and very interesting things, is something that is happening in this decade, where we have also this huge revolution of AI, foundational AI, agentic AI at the same time, right? What is happening is that we relook the way we represent information, right? And think everything we have done so far with computing was you have a problem, you try to abstract the problem in a set of equation, you take this equation, you put on a digital computer. When you put on a digital computer, of course, you discretize the problem, and then you do computation on the bits, right? So that is the way we have used IT to make a difference in business and science so far. Now what is happening is that on one side, AI is transforming the way we do this abstraction. We can go directly in many cases from data to an engine that allow us eventually to solve the problem. For many years we had to go through mathematics, discretization. Now we change abstraction. At the same time, quantum is changing the way we represent information from 0 and 1. Think about all the possible combination on a sphere in a continuous way from 0 and 1, right? That is a representation of the qubit. So you can imagine that simply changing the way we represent information and we abstract reality, this allow us to look at problems with different lenses. And what it means is that, as Sarah was saying very well, there is a new era for algorithm discovery based on this new representation, right? And this abstraction that eventually, in my opinion, is going to really completely change the way we solve problems. We will be able to solve the same problem in a more effective way. And problems that we were not able to solve, right, in a completely new way. And that's why, looking at quantum only as the next accelerator is a mistake. Yes? And there's a mistake also to think about something that is 30 years in the future, because this revolution is happening now while we are speaking.
Well, that's a good optimistic note for 2025 ending.
Yes. So I mean, when I look at this, and I basically, what I think you're saying is that the approach of going and saying that quantum is just going to be the next accelerator is going to be the wrong way of thinking about it, and that that it is going to require thinking about software in a different way, and it's going to think about breaking up the problem space into this stuff, which is really interesting, and but obviously also raises questions in terms of, okay, then how should we think about this? How should we approach to this? Because I think we've definitely as we've looked at compute, and we talked about, the compute scaling, particularly GPU scaling, we've seen that we have seen that model before. We've seen both models. One was we've seen the existing stuff, but faster. We can change the clock speed. And then we've seen, okay, now we have to actually rethink the software and architecture. So then what is the right way about thinking about this? What does the division of responsibility in terms of workloads in relation to between my classical CPUs and then or GPUs, which is different but a variant of that, and then what we see with what's going to operate from a quantum standpoint. What have you learned so far on this journey as you've gone to solve some of these problems that are giving you your framework for thinking about this?
Yeah. So let me give my point of view, and then Sarah can go more on details on what is really happening today with quantum algorithms and their interaction with the classical. Look, you said that very well. We went from a world where CPU were the most differentiated and useful part of the computing ecosystem, right? CPU were the one that were making the calculation, and we tried eventually to create the full system, both hardware and software, to try to maximize the CPU usage. Think about the different level of caches. Think about the blocking in software, right? The parallelism, simply because you wanted to use the CPU more. So then, what happens is that massively parallelism, deep learning, GPU become the most effective part of the computer to solve these problems. So we started to create computers to optimize the usage of the GPUs. It's not that the CPU disappeared, but everything was done to try to maximize the use of the GPU, right? So you went from a CPU-centric to a GPU-centric world. So now quantum come in. Quantum is going to be so differentiating for certain type of application that, by the way, Sarah will tell a little bit more, are very important application, both for science and business. So what I do believe is going to happen is that computers will become quantum-centric. In other ways, what does it mean? It means that the most valuable part is going to be quantum, and we will design the full systems with CPU and GPUs, because all the rest, as I was telling you before, has to come together to try to optimize the usage of this super differentiated piece. And once you are doing it, and if you think about this evolution, what we are going to have is get the problem, which is the part of the problem that has bad scaling in complexity. Solve that on the quantum computer. Then you have all the rest. That means the abstraction, the understanding, the data handling. That is going to be done by the GPU. Partly,
so for a router on top that will kind of partition and break the problems, that router never goes away.
It could, I mean, part of what I keep on thinking, of course, is that we may actually, I was going to say we may end up relying on that router may actually be some form of runtime vibe coding, because you might have to be doing runtime code generation that actually figures these things out if we're going to have to create something that's But anyway, that's a separate conversation.
AI-driven router.
Exactly.
So that's a very fascinating thing, which is a problem is not necessarily a problem of A, B, or C, but typically a problem of A plus B plus C. I think that's what I've learned from all of you. So Sarah, what's an example of a problem that is either quantum-centric or kind of leverages all three piece parts that we have talked about?
Yeah, well, I mean, as Alessandro said, I think we're really envisioning workflows in general being this sort of combined framework, quantum centric, but we're really exploring now how can we optimize workflows that leverage classical for what classical does very well, leverage AI, and have quantum come in for those subroutines that are just really always going to be hard to do classically. And I think the history of algorithms development in quantum has been, we've had these canonical quantum algorithms that were sort of end-to-end quantum, and they showed that quantum can do something with speed-ups over classical for specific cases, for specific problems. But now we're kind of entering a new paradigm of algorithm development, right? We have quantum computers today that can run quantum circuits that are beyond what you can exactly simulate classically. So that means we're doing this very empirical testing and working through new workflows and seeing where can we plug in quantum into a larger workflow and get more out than you could do with classical alone, right? So a lot of our early examples are in that chemistry, material science space where we are running simulations of quantum systems, right? And there are very good classical algorithms for doing those kinds of problems today. So there's a lot of algorithms that approximate the problem somehow, and they can do a good job in a lot of cases. But there are still things that are hard to do classically. So systems where there's systems that are highly correlated can be hard to simulate classically. There are certain problems in various areas of physics where the classical methods don't agree with each other. So then you have to go do an experiment and see what does this material really do, right? Or what is this system? How does the system really behave? So those are some of the problems that we're looking at now in this kind of combined quantum and QPU, CPU, GPU sort of framework. So we've been playing around with new diagonalization methods that use the quantum computer to generate samples that plug into a larger workflow. So these are based on classical methods of diagonalization where you get a set of possible states and you divide them up into subspaces and diagonalize each of them in parallel. And there's a very expensive diagonalization process, but that can be handled on HPC today. But the quantum computer is basically used for proposing better samples. So it's kind of inputs into this classical workflow. So we still have a lot of expensive, a lot of time on the classical side, but we can use a quantum computer to get better samples and improve the workflow.
What is diagonalization good for?
Well, that's essentially what we're doing in a lot of chemistry and material science problems. We're solving for ground state energies. So we have a description of the system. So we have a Hamiltonian that describes the energy of the system, and we have to diagonalize that to find what is the ground state of that system. So this is a problem that maybe diagonalization sounds like a niche thing, but it's actually very practically relevant.
It's relevant also in many other engineering problems, right? So if you want to understand, for example, which are the vibrational frequencies that are important for a given object, you have the dynamic matrix, you diagonalize, and you can find those, right? It's important even in data analysis. So if you take a big set of data and you want to get the correlation, you can get the inverse of the covariance matrix, and you diagonalize, and you are able to find out which things are correlated one with the other. So diagonalization is one of the most, I would say, interesting and general algorithms that you make.
So what we heard, Sarah, from you is we can use quantum to improve or get faster in our HPC algorithms, right? That's what we talked about in this space. But you also have been talking about kind of the inverse, which is you'll use kind of classical AI or machine learning to actually improve your quantum systems. So talk to us a bit about that with respect to weights and parameter selections and other things.
Sure. Yeah, I mean, this is all about like using the right tool for the job and using all of the tools at our disposal to have the most optimized workflows, right? So a lot of the quantum algorithms that we're exploring today are they are hybrids of classical and quantum. Like there's some interaction between the quantum computer and the classical computer, and there's often different steps of the workflow that can be optimized. So one step is how do you take a general quantum circuit and map it onto the specific hardware that you have? And there's details of the hardware on how you can do that most efficiently and most effectively so that you can get the best outcomes when you actually run it on a quantum computer. So we've had an effort on developing AI transpilers for doing that circuit optimization step. And that's something that's not done on the quantum computer itself, but it's figuring out how do you map to the specific qubits on your device in a way that you're going to get the most likely the best result. But there's other algorithms that are kind of they're sort of heuristic algorithms where there's a variational component, and we have some variational parameters that impact how you update the next step in your iterations of these variational algorithms. And your selection of those parameters impacts how well you converge to the right answer, how quickly and how accurately. So we're looking at exploring ways of using AI for tuning those parameters in these variational algorithms. So there's these components of the total workflow where you can optimize the performance, and we're looking at identifying places where classical techniques, AI techniques can come in and make improvements so that we get faster run times or higher accuracy overall.
Yeah. And by the way, this is what we are doing today. Sarah and the team is doing today. But projecting a little bit in the near future, you can understand that if we do have this opportunity to discover and design new algorithms, right, that are completely unknown today, bringing together these two worlds, then you can say probably AI and the new AI that we have today could help us in the process of discovering these new algorithms. I have the problem. How can I best split this in different pieces? Or, as Ed was saying, once this is down on the computer, right? How, even at the runtime level, how could I automatically decide that this optimization, I do it on a classical computer, whereas this other I'm doing on a quantum computer, and bring some of the results back, and then continues to optimize in real time. This is the next revolution that we do believe is going to happen. An investment not only from our side, so IBM, are growing exponentially in this field. That is where the value is going to be.
No, that makes a ton of sense. I mean, I think that was one of the pieces, and as I've looked at this, one of the big questions for me has been, what does the developer journey look like? Because what I've seen is that quantum right now has been in a similar state to where, big data was, say, 10 or 15 years ago, which was, you had, very revolutionary stuff that was being applied for extremely high value use cases, but the people, the practitioners that were involved in it were really, researchers, were scientists. They might be doing applied, it's applied, it's in service of some sort of engineering problem and so on, but it wasn't something that that had yet entered into the programming mainstream. And so that has been one, and I think what's changed really over the last, say, 5 years, last 10 years in terms of big data, has been that things like toolkits, frameworks, emerged, and then of course, what really has changed over the last couple of years has been that now you don't even necessarily need to know how these frameworks work or use these. You use AI coding, and so it sounds like what you're saying is right now we are at the state where we're transitioning from, or at least probably most of the practitioners in this space are experts. They're folks like yourself that have a very deep understanding. There are frameworks, right? My understanding, things like QuizKit and things like that are approachable. But ultimately, there is going to be an entirely new software architecture, and it sounds like AI is going to play a big role within that for letting developers harness these capabilities.
Yeah. Sorry, my cat's meowing in the background here.
Ed is also a cat person, so
I am. I decided to do this from the office rather than at home, so that but otherwise you would see in some of these the cat has made a guest
But
appearance.
Sarah, is your cat the Schrodinger cat?
oh my
Or is
God.
a normal
Well, she's
one?
very much
I hope
alive.
not.
So
It's been observed and it's alive.
Yes, exactly.
yeah. She has lots to say about Qiskit, apparently. Yeah. I mean, I think. Well, I'll start by saying I think there are a lot of resources out there today. I mean, we have certainly from IBM we've put together a lot of tools. So as you mentioned, Qiskit is the open source software that IBM has developed for interfacing with quantum computers. And we have a ton of resources from YouTube channel with lectures on quantum, tutorials on the Qiskit page. So there's a lot of ways to get involved and start learning how to code for quantum. And there's hackathons, there's Qiskit challenges, there's all kinds of entry points. And I think to the point of how are people growing their expertise and what does this journey look like? I think quantum is at a stage where we are still operating at kind of like we're at the algorithmic level. We're talking about quantum circuits and how do you map onto the hardware. It is thinking more at a lower level of abstraction still, right? And I think what we're really seeing is that it's requiring this ecosystem of people, domain experts.
Is it fair to say right now that we are kind of at not even assembly level, but firmware level of programming? Is that the way to think about it?
Yeah, I mean, we're starting to get to a little bit more abstraction. So there are some workflows available that are, we have Qiskit add-ons, which are kind of building blocks that do the mapping part of your program or the solver part of your program. We have third-party Qiskit functions, which are more end-to-end workflows for applications like optimization or like the Hamiltonian simulation pieces. So we're starting to see that abstraction emerge, but there's also still a lot of work happening at those lower levels and a lot of contributions from the community as well. But yeah, quantum at this stage is I think people who are getting involved are really the trailblazers for computational science, right? Like this is the time where we're really shaping the future of the field, right? So we're understanding, what are those problems that really are going to need quantum, and once we have those first things, it's going to expand into new algorithms and new iterations back into the research. So the work that we do a lot of work with partners from different industries industries, from academia, from national labs, like that that combination of domain experts and quantum developers, quantum computational scientists is really what is shaping what algorithms get developed. How do we identify what are the problems that we need to solve in order to make quantum computing useful? So it is I think people getting into that journey and learning quantum from who are familiar with AI, or who are experts in quantum chemistry or computational biology, or have really hard optimization problems that they've been playing around with Cplex, or they've been playing around with AI, and they really know the limitations of those different methods. Like I think there's a lot of opportunity for those folks to contribute to quantum now.
Yeah, I do believe you made a very good, let's say, comparison. But I do believe that at the level of abstraction, what we do have today is what we had, many years ago. You remember with these numerical recipes, right? Where you have these standard representations that yes, you could use and work.
Volume 1, Knut, to volume 2, I forget now which one.
You can use it to try to experiment, but if you want to have that running real performance, etc., you need to do much more work, right? So put it that way. But we still have something to facilitate the users. By the way, you have an idea how many users we do have today on our quantum computers?
200.
Order of magnitude.
Oh,
Gosh.
Do
I know the answer. But I'm just 200 would be an amazing number.
We have many more users than that. I don't know if I have the number offhand, Alessandro.
600,000.
Okay.
Wow.
Okay. There you go.
So simply to tell you that it's not everybody, but it's not 200, right? So you have
that's
3 order of magnitude in between. Yeah.
That is so 600,000 different people, users have come through to presumably do something. And yes, that is super exciting. I'd heard from one of my colleagues that had actually just over Thanksgiving break had taken advantage of that. I guess there's some mechanisms to sign up and actually leverage the hardware, and he'd actually tried some things out, and so I was like, wow, okay, it's really at that level where people can go and play with it. So how soon? So I guess if you're doing some form of HPC or scientific computing, you're probably already sort of this is probably already on your radar. You're probably, in fact, you may be chomping at the bit for doing more, literally, on these things. And then for more, and then I guess over time, where will we see this go into? Do we have any sense of sort of over the, say, next 10 years, which use cases, starting from, it sounds like obviously if you're doing like drug discovery, pharmaceuticals, chemistry, things like that are already dealing with quantum physical processes, you're probably already looking at this, but where how does it play out? How does it?
Yeah, does somebody who's doing fraud detection and commercial application, would they get affected? Would they benefit?
Mm-hmm. Yeah. I mean, like I said, we're working with partners across many industries. So not just these chemistry and material science problems, but I think there are real applications that are in optimization problems. So this is very active work, and I think the optimization space is one where it's not the same argument as you need a quantum state to represent a chemistry problem. But we know that there are problems that are hard at relatively small scales classically, and we're putting a lot of effort into really rigorously benchmarking between different approaches and understanding where heuristic quantum methods can offer value in the near near term. So optimization problems, appear everywhere. Logistics, portfolio optimization, scheduling, all kinds of things. And
so, for example,
that's
what
the space
HSBC has been doing with us.
So we did some work with HSBC, looking at a trading problem. We actually were exploring quantum machine learning methods with them, and that's another category where again we're exploring things in kind of heuristic, empirical ways of seeing if we can leverage these quantum representations in a learning framework. We're looking at kernel methods, but with quantum kernels, things like that, and seeing if you can get some value from quantum over classical. So that's what they saw working with us on a quantum workflow, that they're able to make improvements over their standard workflow. And the last category that we're looking at is differential equations, and there's I think a growth of work in the theory space on algorithms for differential equations with quantum. So we've posted a paper, a preprint recently on an end-to-end quantum algorithm for stochastic differential equations. So would be relevant for solving Navier-Stokes equations and things like that. And that's again an application hugely impactful. Some of the hardest computational problems today are solving PDEs, right? And that's also a space where we can imagine quantum and classical working together, because they could solve problems at kind of different scales, different resolutions, and have that kind of hybrid framework.
So clearly, Sarah, just on that one, right? For example, if you listen to Naveen Rao, right, who sold Mosaic to Databricks and are now spun out. He's doing a company called Unconventional. Very believes that classic chips are not going to be able to solve this kind of Navier-Stokes problems. Right? So kind of a different approach. Can I use analog chips and make that happen? So this is really fascinating. Because if I can just tie a ribbon to what I heard today. We've always been fascinated with whether quantum computer will be realizable, not realizable, and qubits and error correction, right? And all the foo-bars around it. And so there is a lot of progress being made at IBM and at a few other places. And there's general belief that will happen. Right? It's not a matter of everything is a decade away. But what you are seeing now, therefore, with that assumption, that happening, really the energy needs to shift to the software and algorithms, and how do people actually design stuff to it and use stuff to it. So it's really fascinating that you need to kind of carry. In the beginning, hardware was the hard part of it, but now really it's turning out that software is where the real action is going to be, while hardware continues to be. Is that a kind of a fair way of stating this?
Yes, and by the way, you were mentioning the HSBC problem, collaboration, right, and usage of quantum computer. That is an example where a company, a financial company, simply due to the fact that quantum computing was giving to them a reason to try to rethink algorithms and software, right? And in this rethinking, they come up with an implementation of calculating the probability that a given stocks will fill order of stocks will fill for a given price 30% better than what they were doing before. Independently by the fact that these were really coming by the fact that quantum was there, the push to rethink the algorithm and this heuristic approach that Sarah was mentioning helped to move the field forward. And that is a very exciting part, right? We are trying to bring these things together, and while we are doing it, we push the field of computation to the next level. That is a very exciting part.
So many different problems got solved when people were trying to prove Fermat's theorem, right? Even the Fermat's last theorem itself was the goal, but then a lot of hard problems got solved. That's absolutely fascinating. Hey, listen, We are about nearing the end of time here. So, folks, thank you so much for demystifying and for being optimistic. And next time when somebody asks me AI and quantum, or ask any of our listeners, we will sound at least for 10 minutes intelligent because of the conversation that we've just had. So, fantastic. Hey, Ed, any parting thoughts?
Well, I think Anant, for you and I, between now and the next session, we need to actually play around with Qiskit and do something. If there's already 600,000 developers.
I thought I'd take from 200 to 202. At least it will be 1% change.
Yeah, well, given given how far off you were, we need to dig into this stuff and play around with it. So I look forward to seeing Anant, your hello world, your quantum hello world.
Hey folks, thank you so much.
Yes,
and absolutely
amazing
talking to both of you. Thank you.
Thank you.
Have a good day.
Thanks.
That was absolutely fascinating. I mean, to kind of think through not only what the software revolution is, algorithmic evolution, how AI can help quantum, how quantum can help AI. It's going to be really huge set of new innovations that will happen.
Yeah, no, I absolutely think that's the case, and I do actually suspect that that AI is going to be a big part of making it possible to build this software. Even just while we were talking, I had Claude write me a Qiskit hello world just to see what it looked like, and so yeah, I mean, honestly, which I think is interesting. I mean, honestly, like, and if you which carries across a lot of other domains, which is that as we may not have that same software learning curve because it may just be possible to help bridge the gap that way. But certainly the stuff that they were talking about, I think this is, I mean, that was the question, and that we spoke with them beforehand and again during the course of this, which is how soon does this become a key part of, particularly for a lot of things like fraud detection and so on. I think the answer is going to be a lot sooner than most people expect. So I think this is really exciting. I'm glad we had the opportunity to have them join us. I learned a ton from it.
Yeah, I remember being asked about a year back by some analysts, how do AI and quantum kind of come together? And I kind of I didn't quite say it to the analyst, but I kind of made a comment to one of my colleagues that to me it sounds like we are mixing and matching. In New York City, you can get Ethiopian Burmese cuisine because the husband is from Myanmar and the wife is from Ethiopia. But they're just kind of together. So I made a slight remark which said that I believe that these are just two words that are thrown together. But as I've kind of studied in our conversation today, it really is that there'll be a lot of synergy on the two sides. Whether AI will improve because of quantum will improve because of AI, but the development will improve because of this, but the fraud, we don't exactly know what the shape will be, but the two will actually fundamentally, along with classical HPC style computing and classical computing, will play a fundamental role in this new world.
Exactly. Yes.
Quantum supercomputer. Yeah, exactly. Okay,
yeah, exactly.
Awesome.
Okay. Yes.
So, go ahead, Ed.
Go ahead, Ed. No, so I was going to say, so that was our concluding podcast for the year. We'll be back in January, and we have Peter Starr, who's going to be joining us, and so that's going to be exciting.
What will Peter talk about?
Well, so Peter has been doing a lot of stuff from dealing with unstructured data, and his approach, which I'm excited to have him here talking about, is he's really been one of the sort of key figures from really, I think, the new generation of what's been happening within research. He's created the Dockling open source project, which many people use. Folks on Hugging Face and many frameworks and so on. If you're building a RAG system, if you're taking apart tables and PDF documents and doing anything where you're dealing with unstructured data, there's a very good chance that you're directly using or one of the dependencies that you're using is pulling in this model for ingesting unstructured data. So looking forward to having him here talking about what he's been working on and really just getting his point of view of how this stuff, how does this world of research get into the open source that's just being used everywhere. It should be a great conversation.
It'll be an absolutely fascinating conversation, Ed. It's just been absolute pleasure to welcome you back into IBM, middle of the year. And we've had a lot of fun. And of course, arguments between us and with other folks. But we've also kind of kicked off this context window podcast, which I think is delivering. One of our listeners kind of corrected me when I said there may be only one other listener, and she corrected and said, no, she believes there are more than one. So I think that's very good. Again, we don't know whether it's 200 or 600,000. It's somewhere in between.
Well, let's hope. Hopefully, look, we in our attempts to become AI influencers. Let's do that classic thing. Like, please like and subscribe. Give us some feedback in the comments. Let us know that you're all watching us through the end. We're going to keep doing this regardless because we're having fun doing it. But looking forward to hearing from folks as to what you like and don't like and what we should talk about in the coming year.
Ed, and to all our audience, have wonderful holidays. It's just been a pleasure talking to you, Ed, talking to our guests, and then talking with all our audience. So thank you for